Hill analysis. More details of this are in 14.2, page 655. It is a generalized model for understanding cooperative binding when you have n number of ligands binding to a protein. Okay? Instead of like one binds, we have several. Okay? And it assumes that all the ligands bind to their target in a single step. So this would be like 4 oxygens binding to hemoglobin at once. This doesn't happen. That's not real. They bind one at a time, and it is positive cooperativity. Once the first one binds, it gets easier and easier for the others to bind. But for this generalized initial sort of introduction to what we're talking about, you could write this as you have your protein plus n number of ligands here. There, n is sort of a stoichiometric number, and then they're complexed now. Okay? Hill analysis, commonly used, physically implausible, but we still use this model, okay? The dissociation constant would then, if you treat this like a stoichiometric coefficient, you're going to raise the concentration of the ligand to this n coefficient. So we have free protein, free ligand raised to the n over our complex concentration. And if we solve for the fraction of sites filled, we get something called Hill equation. Okay? So the fraction of sites that will be filled is given by this relationship here. And if you plot sort of your fractional saturation versus ligand concentration, you get something called a Hill plot. And again, you have some shapes that indicate how many ligands are involved. Okay? So you could have your typical sort of hyperbolic curve, your regular binding curve is shown, and that would be an n equal to 1. And then we have these increasingly steep sigmoidal shapes. This is sort of a generic figure showing the relative differences in the shape. For red, this is sort of an n of 2. So we'd have 2 ligands binding, n of 4, or n of 8. But if you had actual numbers on here, you could take the slope of your curve and actually tell me what n is. So be prepared to maybe do something like that. If there were numbers on these, and I said, hey, there's a curve, how many ligands binds to this protein? Get the slope off of that region in between, okay? And that n value tells you, oh, this thing binds 2 ligands, 3, 4, whatever, okay? Single proteins can have multiple ligand sites. Like I said, hemoglobins are a popular example throughout this course. A more common situation, rather than like a single protein that has multiple ligand sites, is that it's a single protein, but it'll have different subunits where each one has a site. That's more common, okay? And then there's communication between the subunits, okay? Hemoglobin is sort of the quintessential example of allosteric regulation. It has 4 very similar looking subunits, 2 alpha, 2 beta. They each have a heme group. They each can bind an oxygen molecule. What hemoglobin does in the body is it increases the oxygen carrying capacity of the blood. It helps transport oxygen from the lungs to the tissues. Okay. So here's a textbook illustration of that. I hate this figure. It's creepy. There's better ones on the internet. So in your lungs, you have some oxygen that you've inspired. And so you've raised the partial pressure of oxygen in your blood. And then here we have our hemoglobin with its 4 iron heme groups, each able to bind oxygen. Okay, it's going to carry the oxygen down to tissue such as muscle. So we might call this our oxyhemoglobin because it has oxygen attached. It will release the oxygen. Myoglobin hangs out in the muscles and will store the oxygen. Okay. Myoglobin is like a single subunit of hemoglobin. And then we have now deoxyhemoglobin. It can pick up CO2, okay, that's in your muscles and carry it out to the lungs, and then you can breathe your carbon dioxide out. Okay. Myoglobin is our monomer, and it acts as an O2 reservoir in muscle. Here's just another still not great illustration of this situation. Like I said, if you Google this, there's like a million versions of this figure. But again, what we can see here, I picked this one simply because it sort of draws it as hemoglobin and oxygen, like going to hemoglobin-oxygen, almost like a reaction here. It's picking it up. In the lungs, your heart pumps it out to the rest of your body. It gets exchanged into your It'll release the oxygen. Oxygen can get stored in muscle tissue. The hemoglobin will now pick up CO2 and carry it back out. This link here is a nice little explanation of partial pressure. It is the pressure exerted by a given gas in a mixture of gases. Atmospheric air has way more sort of percent oxygen than CO2, so the partial pressure of oxygen in sort of ambient air is 160 millimeters of mercury, where CO2 is really small. And then once you kind of see over here, once it dissolves in the blood, it's a little bit lower than air. There's a lot of other stuff going on in your blood. Over here in your venous blood, this is even switching now. You'll have a higher concentration of CO2 in your blood than O2. So like I said, I recommend reading this if you want some more information on interpretation of partial pressure. It's directly related to concentration. So for the purposes of this class, because I'm never going to ask you to calculate it or anything, maybe just use it and interpret it off of a plot. It's related to concentration. The higher it is, the more O2's in that blood. Makes sense. Okay, so this is a similar figure here showing you differences in partial pressure of oxygen versus CO2 in the air, in arterial blood. Hemoglobin is here where it's picking up a bunch of this oxygen because you have this higher amount of oxygen there. It'll pump it through the heart, transport it to tissues. It'll drop the oxygen off where there is sort of a lower concentration, picks up CO2 that's now higher, carries it up and out. So with that, this is an actual exam question that I wrote for fall 18. So I'm not going to give it to you again, but I'd like you to take a couple minutes and talk about this with the people around you. Okay, so it says, use the information provided below to answer the following questions. The y-axis on this graph is fractional saturation, or F. Okay, the x-axis is partial pressure of oxygen in torr. 1 torr is 1 millimeter of mercury. Doesn't matter, I'm not asking you to convert any units. Okay. Leave your answers in terms of partial pressure of oxygen given in torr. You do not need to convert this unit to a molar concentration, and this is simply because it's a directly proportional relationship. So again, notice here you have some KD values given in torr. We usually are going to report things in molar. That's fine. Actually, I think I took one line off of here that asked you to get a KD, so I was asking you to give it to me in torr. Don't try to do anything with it. Okay? So why don't you guys take a couple minutes, talk to the people around you about all 4 of these. Estimate the total percent of oxygen binding sites of all the hemoglobin molecules that would be occupied in lungs. If lung has partial pressure 100 torr, then it asks about what percent you think would be bound in muscle. Is there cooperative binding? I already gave you the answer to this, but that's okay. Make sure you could explain it. And then why is myoglobin not suitable for oxygen delivery? Okay, so take a few minutes and talk about those, and we'll come back and answer them.